rotation. I have another illustration from the red book. This one. That is not easy. Well, it's too small. That's the wrong. Oh, okay. This one. Yeah, it's just to illustrate we rotate an object. The flower pot is turned around the z-axis in this case. Now these, as you notice, are OpenGL coordinates, so the z-axis is pointing that way. What rotation is not moving anything, and it's also not taking place anywhere else than around the origin. So of course we can rotate stuff around its own axis somewhere in space. Of course we can do that, but that's not what we mean when we say the word rotation. Rotation means always rotating around the origin of the coordinate system that stuff is defined in. In this case, the flower pot is defined its own local coordinate space, and the rotation does this. It rotates it somehow. It could be around one of the other axes or some arbitrary axis. That could be all different, but it's always around the origin. So I'm not going to define exactly what rotation we want to do as we did with translation, because it's not so simple to do with rotation. There are different ways of defining a desired rotation. So for now we're going to draw something that's actually very similar to matrix that we put before. We put 9 little dots signifying these 9 values are interesting to the rotation. They should be controlled in some way to achieve the rotation we want. So this is really the only way we can talk about a generalized rotation matrix, is to draw this. And remember that we don't call this part the rotation part, the 9 values here, we call it the linear part, because it can also scale and do other things if we arrange the values in a different way. But if we, in this place here, we put a 3x3 rotation matrix, which we calculate from the desired rotation we want to do, then it becomes a proper rotation. Oops. This here. And we do that on the next slide here, so I just put a little piece re-on. Or rather, we do it in one of the many ways that this can be done. More specifically, we try to do exactly what is done in this image, that is rotation around the z-axis. And that means that the object's z-axis, its own local z-axis, doesn't move. So any vertices that are along this z-axis, they actually stay in the same place. Everything else rotates around it. That's what we mean when we say rotating around an axis. It can sometimes be confusing because what the rotation about the z-axis does is it modifies the x and y coordinate of every vertex. So if in case they are 0, which means they're on the axis, then they're not modified, or others are modified. So the z rotation actually modifies x and y. Yeah. And there's a special matrix for that. Use the z-axis rotation matrix. We have one here just for rotating around the z-axis. And it looks like this. Now we have some nice trigonometric functions. Hope you can remember what they are. I have just one moment. This Photoshop. Can't get rid of it. There. There. Just to put. There's too little space on the screen. There it is. And a good rule for these rotation matrices is to remember the basis vectors. So they can actually be regarded as, I'll put this in red, like this column here, or the first three values is like the x basis vector of the local coordinate system, the y and the z. So if we rotate around the z-axis, then these these elements here of sine and cosine, these trigonometric functions, go in the other two. So they go in the x and the y. And in the same way, we can construct matrices to rotate around the x-axis and the y-axis. So on the z basis here is simply the z-axis 0, 0, 1, which is points towards z. And we're going to do a slide with these other two. This was the set. I'm gonna try to do what I just described. The x-axis, so here it just goes a 1 on the x. A bit more space. It's a little slightly different because the minus sinus is in the other place. Actually, it's the same place here, but then the y it's sort of the other way around. So that's a little thing to remember. So not minus here, but plus. Here then is the minus. Oh no, that's wrong. Here goes a 0 because we need the 1 at the y-axis. Here is the minus sinus. Now you probably guessed this, but the theta is of course the angle that you rotate. It can be any angle. So you can rotate any angle around any axis this way using these 3 matrices. And I think doing one more. Just check that. I think we should do one more scaling as well. No. No. Yes, please.